Hi and hello everyone. Welcome to the solo presentation. It's such an honor for me to be able to participate in the 16th annual IEEE International Systems Conference. So the title of our study is Design and Accuracy Assessment of a Multi-Input Single-Ended Primary Inductor Converter for Highly Efficient Output from Hybrid Sources of Renewable Energy. I am Tahmin Mahmud, currently working as a research assistant at the Control and Applications Research Center, Breck University. Now let's take a look at the agenda of today's presentation. Initially, I'll talk about the problem statement, the motivation of our study, and then slowly and gradually I'll delve more into the theoretical aspects of our study. For example, the DCDC converters, CP converter, the meso-CP topology. And in the following section, I'll talk about the proposed system. I'll also introduce the prototype of our study, how we built the meso-CP circuit, and also the meso-CP circuit. In the next portion, I'll describe the practical field test analysis. In the final part, I will also talk about the software simulation and as well as the result analysis. And thus, I will conclude my presentation by describing the future work of our study. This article was published in the World Economic Forum portal. It says, life for millions in Bangladesh is being transformed thanks to this simple solution. So what's this simple solution? The simple solution is to opt into renewable energy. Renewable energy projects can help rural communities get out of the poverty trap if they are feasible and well implemented. Bangladesh is extremely vulnerable to climate change due to its topography. According to the Global Climate Risk Index, it's one of the 9th most vulnerable countries in the world. So on the other spectrum, the opportunity to build green infrastructure from the ground up is the biggest challenge here. So this is why everyone thinks that renewable energy sources might be a realistic solution to this country's energy issue. The main problem associates the current world is the scarcity of fossil fuels and as well as the energy crisis. The negative impacts of fossil fuel creates threat to global pediatric health and equity from fossil fuel combustion. So this is an article which was published in the Cambridge University Press. It says climate change and fossil fuel, an examination of risks for the energy industry and producer states. So they have said that climate change, rising oil costs, global warming, and the scarcity of the fossil fuels have heightened interests in the renewable energy resources. So we thought that why not settle on solar photovoltaic panels and electrical power generation via bicycle pedals. So we believe that smart and effective implementation of this system can gain popularity and people's trust within a amount of time. So here comes the main motivation of our study. We always wanted and look forward to work on a clean energy solution. So this is why we built a system that has zero emission and which is also cost efficient. So and lastly, we settled on an affordable energy harvesting system for distant islands. So our target audience is the rural people who lives in distant islands. In our country and in the subcontinent area, the government and local stakeholders are already investing more and more in the renewable energy, and this is a clear evidence that says Bangladesh is eyeing rapid growth in the renewable energy by 2050. So this is a diagram that shows the annual growth of renewable electricity generation by source from 2018 to 2020, and we can see that solar PV always dominates with respect to all other renewable energy sources. And renewable energy costs declined rapidly over the last 10 years, and solar photovoltaics is the most dominant among all the other renewable energy sources. So now here comes the question, what is a DC-DC converter? A DC to DC converter is an electric circuit or electromechanical device that converts a source of direct current from one voltage level to another. It's a type of electric power converter. DC-DC converters are used in a wide range of applications. DC-DC converters have a multitude of purposes in the automobile industry. Boost converters are utilized in hybrid electric vehicles. Adaptive control applications such as those are found in spacecraft, aircraft, airbuses, jets, and also robotics applications. So in the industry, we can see that we have different topologies of this DCDC converter. For example, the buck converter, boost converter, buck boost converter, and also a flyback converter. And we also have another converter, which is CP converter, and there are many more converters. For example, two converter, cyclo converter, and matrix converter, etc. Solar panels typically provide a low amount of voltage as their output. The boost converter is needed in order to achieve a higher voltage that is required by the majority of loads. So this is where a DC-DC converter is can be used to ensure that a solar panel produces the greatest possible amount of electricity. Now here comes the CP converter. The single-ended primary inductor converter operates on both the step up and step down principles. Two inductors are used to either buck or boost the input voltage to the output voltage, and the output voltage is not reversed in polarity as a result of this configuration. So the CP converter's features are non-inverting output, gracious response, low noise operation, flexible input voltages with stable output. The mesocepic topology. A multi-input converter is essentially a circuit structure that integrates various input voltage sources with varying voltage levels and delivers an output DC load to a single output voltage source. So if we simplify that, it means our hybrid topology is a single-ended primary inductor converter based multi-input single output converter for photovoltaic based bicycle dynamo system. The configuration shows that the number of ports may be increased or decreased even further by connecting or detaching the extra pulsating voltage cells depending on the availability of the power and data input sources. Now the proposed solution. The proposed solution is robust and it's an off-grid solution. We can connect multiple input sources at the input side. Our system has a long-term backup. Effective voltage gain is also incorporated in the system, and the overall system is a battery-less design. Here comes the system block diagram. So from the system block diagram, we can see that we have two input sources, the solar photovoltaic and bicycle dynamo. The solar photovoltaic is connected with an MPPT charge controller to stabilize the output voltage, and it is then further fed into the mesocepic converter circuit. Now, the bicycle dynamo output is controlled by a PID controller, and then it stabilizes the voltage, and then it's being further fed into the mesocepic converter circuit. And at the load end, we can connect anything, and for small scale measurement, we have connected a 10-watt light. The prototype design bicycle dynamo. The dynamo generated power is harnessed as a form of electrical energy converted from mechanical pedaling power of a human. A bicycle dynamo works by using a magnet to transform the revolving wheel's mechanical movement into electric energy. A permanent magnetic field is wound with insulated wire coils in the dynamo. When the magnet rotates, it creates a changing magnetic field, which causes the wire to generate electricity. So in our bicycle dynamo, we are incorporating a hub dynamo over a bottle dynamo. The hub dynamo is more efficient over a bottle dynamo because they are not impacted by weight circumstances. And one of the most crucial parts of this bicycle dynamo is that we need to maintain the pulley ratio. So these are the outdoor test dataset that we generated from the bicycle dynamo. It shows the change of current with respect to speed. And this is a graphical representation of the speed versus current. That means when we are giving more speed, we can generate more current. So for the solar PV panel, we collected the standard testing condition parameters. We calculated the electrical efficiency of our solar PV panel by using this equation. And for the source, we are using a 10-watt 12-volt sun power solar panel. Although we had the STC parameters, we opted to calculate and investigate the real-life scenarios of our solar PV panel. So this is why we decided to calculate the open circuit voltage and short circuit current. We also measured the cells temperature using infrared temperature meter, and the temperature was also measured using an ambient temperature meter. We also collected the GFS data of the 20th September 2021. Apart from that, we also collected some meteorological data for the solar PV panel, because the output of the solar PV panel is heavily dependent on other aspects like the wind speed and the average relative humidity and the monthly rainfall, and also the longitude and latitude position of the district. So we decided to collect these data from the meteorological report of Bangladesh. These are the outdoor test results of the solar PV panel uh, that are described in tabular form. We have VOC in time, ambient temperature in time, ISC in time, and also the cells temperature in time. So if we plot those data sets in graphs, we can see that these are the graphical representation. So although we had some anomalies in the data, because it was a rainy day, and we think that summer is the best time to study the solar PV panel. Now here comes the prototype design of our SysOcepic topology. We decided to build the SysOcepic circuit using an Arduino Uno. We also used a Schottky diode of SR540 before the load. We used two inductor coils, and our power MOSFET is STP55NF06. So you can see that the input voltage is recorded as 12.22 voltage, and the output voltage is adjusted to 57 volt. So we studied the boost mode operation of the SysOcepic topology. Now in the next part, we can see that how we compared the MesoCepic boost mode with respect to the SysOcepic boost mode. So here we can see the practical field test result, the voltage gain with varying duty cycle plots, and the efficiency and the duty cycle plots. So here comes the MesoCepic topology. The suggested model is having a PV cell at the input side. PV cells are classified into two types: pulsating voltage source cells and pulsating voltage load cells. The suggested model is having a PV cell at the input side. So here we have two sources. One is our solar PV panel, and the other is one is the bicycle dynamo. So our MesoCepic topology works on this algorithm, which is when one source dominates over the other source has less contribution to the overall topology. That means, for example, during daytime, if our solar generates more power, then we don't need the bicycle dynamo. And during the nighttime, when the solar PV panel cannot generate enough power, then we can use the bicycle dynamo as the main source. So these are the main components and parameters of our MesoCepic topology. We used LC filters, which are the most crucial parts of our MesoCepic topology. And we also used power MOSFET S8050 as the NPN transistor. We need to stress on this fact that the gate driver circuit is a very important aspect of the design, because gate driver circuit can optimize the output voltage, and a driver stage is crucial while working with a high-speed MOSFET switching and higher frequency ranges. So the driver stage can steer the overall performance of the voltage conversion process. So it's very important for better accuracy. We also created a reverse voltage polarity protection for our circuit. These are the practical field test results of the MesoCepic topology. The maximum output was calculated as 53.3 volt, while we give input as only 12.1 volt. So the switching frequency was 32 kilohertz. And these are the other tabular form of V gain and D2 cycle and efficiency with varying D2 cycle. So these are the graphical representation of the MesoCepic topology. You can see that the gain of our MesoCepic topology crossed near 4, and then the efficiency also crossed 90%, while we have the D2 cycle to nearly 80%. Now here comes the most important part of our study. We decided to execute the software simulation using MATLAB Simulink. So we have PV array block and MPPT algorithm block, and we also have a mathematical model of the bicycle dynamo. So this is the hardware circuit of our MesoCepic circuit. And by following this hardware circuit, we decided to develop the mathematical model using MATLAB Simulink. An MPPT controller has has been employed here after the voltage source, and which is being further fed into the mesocepic circuit. And we are also using a bicycle dynamo source. A DC machine was used for the dynamo function. One of the pins of this DC machine has been utilized to provide input from the form of RPM, and we calculate the rotating speed in radian per second in our simulation. A new feature has been also added to allow for the measurement of metrics such as rotational speed. The remaining two pins are utilized to supply power in the main circuit that has been generated from mechanical energy. So here we can see that the output of this bicycle dynamo is further being fed into the mesocepic circuit. But here we have used a feedback system for the bicycle dynamo because it's really crucial, because the voltage that we obtain from the dynamo is proportional to the rotational speed. So to stabilize the output of the bicycle dynamo, we used this feedback system. Now, here is the video demonstration of our software simulation. Here you can see the output of the bicycle dynamo. Now you're going to see the output of the PV panel, and now this is the output of the mesocepic topology. So the output of the mesocepic topology was nearly 64.5 volt in our software simulation. So we calculated output results for summer scenario and also the winter scenario. It is to note that the solar irradiance data was collected from the SWIR data, and it is then further being fed into the solar PV panel. That is why we were able to compare the summer and winter scenario. So now here comes the power sharing between the PV panel and the dynamo. The power sharing is an interesting result from our software simulation, and we can see that during the winter, the dynamo power is the orange marks. The dynamo contributed more than the solar PV panel, because in the winter, almost during the foggy scenario, the solar PV panel cannot produce enough power due to the absence of sunlight. So this is why we had to incorporate more power from the dynamo, and the opposite can be seen in the summer, because in summer season PV power was dominating. So the advantages of the MISO over CISO is that it's cost effective and feasible solution. It's cost effective because the LC filter is small. We can analyze a large voltage increment using the mesocepic topology, and it also incorporates effective combination of a variety of other renewable energy sources. So now here comes the most important part of our study. They are the future work. As a part of the future work, we can combine national grid with the mesocepic topology. We can also introduce fuzzy logic controller, and we can also establish more than 2 renewable energy sources in the mesocepic load. So if we talk about more about the fuzzy logic controller, an intelligent fuzzy logic controller system can be designed as an energy management system for this prototype. So it's basically an intelligent management tool based on switching technology that can automate the input sources connected to the load. So it's still under development phase, and we are currently working on that to maximize the supply from the solar panel and save up maximum energy coming from the national grid. The logic controller can play a vital role, and it can save up to 80% energy from national grid during daytime. So a rule-based control of this fuzzy logic controller will be a suitable method to gauge the load demand at various times throughout the day and night. So our system addresses the sustainable development goals, such as responsible consumption and production, affordable and clean energy, climate action, and the sustainable cities and communities. To summarize, I must say that we have designed a hybrid topology of an off-grid energy harvesting system by integrating solar photovoltaic module with bicycle dynamo generator. So our system adopts a DCDC multi-input single output, single inlet primary indenter converter for isolated islands. For boost mode operation, we constructed a conventional CPIC-based CISO topology initially and compared its performance with our suggested hybrid architecture of the CPIC-based MISO converter system. The prototype of the suggested hybrid system was created following an optimal design technique for small-scale performance analysis. Our proposed meso-SEPIC circuit is intended to function at a practical input voltage of 12.1 DC volt, and it provides an estimated output voltage of 53 volt at the load side. So to get the maximum voltage at the output end, the operating duty cycle for the proposed converter was recorded as 81.49%, the gain of 4.4. From the hardware analysis and field test data, we determine a 91.6% efficiency rate for the suggested prototype. With this, I conclude my presentation. Thank you, everyone.